Hi, I'm Benjamin, and I worked on bowling strikes with trajectory optimization. First, a brief introduction to bowling. In this sport, the objective is to roll a bowling ball down a lane and knock down as many of 10 pins as possible. A strike refers to knocking down all 10 pins with a single throw. The motivation behind this project was an automatic strike bowling ball I found on YouTube. In this video, the authors hollowed out the inside of a real bowling ball and replaced it with a pendulum that could be controlled by a remote to swing from side to side. The authors were able to use this bowling ball to roll strikes, but there were some caveats. First, I wouldn't call this sort of bowling ball truly automatic, in the sense that a person needs to be actively controlling the remote for the entire duration of the trajectory. And secondly, the ball only works well at slow speeds, about 3 times as slow as a professional bowler would actually bowl a ball. So what I did in this project was simulate a bowling ball equipped with a single actuator inspired by the automatic strike bowling ball. The actuator has the ability to move the center of mass perpendicular to the direction of motion of the bowling ball. I attempted to compute trajectories where the ball moves as fast as a real bowling ball and satisfies the following constraints, including that the actuation input is bounded, the ball avoids obstacles that can be specified by the user. That is the red circles in the diagram above. And most importantly, the ball knocks down all 10 pins. My approach was to split the trajectory of the ball into 2 phases. In the first phase, I used simplified equations of motion and run direct transcription to compute the actuation input for every time step. I made some assumptions, including that the ball is symmetric about its center and doesn't slip to make this more tractable. In the second phase, I used Drake's contact model to simulate the ball colliding with the pins. I was able to successfully generate these trajectories and create 2D and 3D visualizations. This 2D visualization, you can see that the ball waves around 2 obstacles and ends just before the pins. That is at the end of phase 1. And in the 3D simulation, I simulated both phases. As you can see, all 10 pins were knocked down. One thing I was unable to get working in time, but would be nice to have, is finite horizon LQR to stabilize the trajectory of the ball. However, this turned out not to be necessary for the trajectories presented in this video.